With that, let me introduce Daniel. So first and foremost, I want to say that Daniel has actually been quite instrumental in just getting this class together. Many of you folks obviously don't know this, but when I was actually thinking of how to structure the class, and even before we got all the TAs and staff and everything involved, Daniel was actually hopping on many calls with me just for the heck of it, and giving very valuable input in terms of like how to structure it right from the beginning all to the end. So I think we must have had at least like about 3 or 4 weeks worth of calls. So Daniel, thank you very much. And actually, the students, if you folks feel like you're learning stuff, it's also in part because of Pete and Daniel who've been contributing all that input. Just wanted to mention that. And so Daniel actually worked at Google, so he was actually one of the people who contributed to TensorFlow. So on that note, I'm gonna leave it to Pete. Maybe you can chime in because you clearly worked with Daniel, and you obviously, Daniel, for the folks who might not recognize, actually wrote the TinyML book with Pete as well. So Pete, I'll let you do a little bit of intro here, please.
Yeah, no, Dan has been, really instrumental in actually making the TensorFlow Lite micro framework happen. He not only worked on the book with me, he actually managed to get a lot of the examples actually working. We had a lot of work to do around actually trying to get all of the things with speech and vision and accelerometers actually going. And Dan really actually did a lot of the engineering, as well as working on documentation and everything else that he really was an amazing sort of powerhouse helping drive the framework forward. And now he's at the Edge Impulse, where he's actually helping to kind of help a lot more people do the sort of things that he's he was really instrumental doing with a lot of the examples in particular, actually helping gather the data, which is such a massive, I'm sure he's going to talk about that, but also just kind of the whole end-to-end process of getting an ML application working, which is so much more than just kind of, even just getting a model working. So yeah, I'm really excited to hear what he's going to be talking about today. And yeah, he's really one of the key driving forces behind this whole TinyML movement.
BJ, you're muted.
Thank you, Kobe. With that, Daniel, I'm going to turn it over to you. And one of the things before we get started, I'm super curious, and I'm sure the students are going to be super curious too, is a little bit about tiny farms and what that is all about. I've been meaning to ask you that forever, and for once I remembered.
Oh, awesome. Well, I'm going to try and start, even though I feel all shy and embarrassed now after a far too glowing introduction. So thank you very much, BJ and Pete. While I collect my thoughts, let me share my screen. All right, so hopefully you can see my my screen here.
Yeah.
Okay, awesome. So I'll talk about tiny farms in a second, but to begin with, what I want to talk about in this session is the idea of MLOps. And I'm not sure whether that's something that's a familiar term to many of you or something that you've never heard before. It doesn't matter either way. It's pretty new anyway, so it's unlikely that many people have got a huge amount of experience in this globally. But we're going to be talking about this. So my name is Daniel Situnayake. I'm currently working as a founding TinyML engineer at Edge Impulse, which is a company I'll tell you a bit more about. So actually my first slide is this picture of me and Pete, which was a super fun moment at this O'Reilly conference where we got to sign early release editions of our book. I won't go into all this bio because Pete and Vijay already covered it. But basically I've been working on this TinyML stuff. It's like, I don't know, when you will find in your career, you will find at some moment you'll come across the thing or the technology that you realize is just perfectly suited for you and for everything you're interested in. And for me, embedded machine learning was this thing. It kind of brought together everything that I was always fascinated about machine learning on one side and embedded engineering on another side, and then thinking about usability and developer experience too. So it's just my favorite thing in the world. Tiny Farms is, so to go back in time, before I was working at Google, I've been a software engineer for a number of years at various companies around Silicon Valley. For some reason decided that it would be a good idea to start an agricultural technology company. And we were looking at basically what are the ways that you can deploy using modern technology to improve the production efficiency of agriculture. And one of the ways that you can do that is by farming insects. And so insects are extremely efficient at converting feed, so carbohydrates, starches, into protein. And you can then use that protein in human food, or you can use the protein in animal feed. And so perhaps it could help do away with some of these horrible things that exist in the world, like that we trawl the ocean for small fish and then grind them up and feed them to cattle. So started this company, Tiny Farms, ran it for a number of years. We raised a bunch of money, built a big insect farm in San Leandro in the Bay Area, which was producing a couple of tons of crickets a month. Learned a lot along the way about all kinds of things, many of which I didn't really want to learn about, and others that ended up being kind of relevant to what I'm doing now. So we did a lot of stuff with embedded sensing, and we were using machine learning and computer vision tools to try and understand what was going on with the insects on our farm. So that's a whole other life. Luckily, these days, I don't ever have to see crickets day to day. But that is something that I did, and it's something that sort of informed a little bit of what I work on today. So I guess we've got about an hour, right, Vijay?
Yeah.
Okay, perfect. So I put together roughly probably about 45 minutes of stuff I want to talk about, and then we have loads of time for questions as well. So what I want to do is, first of all, talk about what is MLOps, like introduce this concept and talk about why it's necessary and why it's useful, and then walk through some of the features that an MLOps platform might have. And then I'm going to show how you can train TinyML models using MLOps tools super fast. So whereas if you've walked through the TinyML book, you've probably seen this sort of like a whole load of different tools and different threads of different types of stuff that all come together to allow you to train and deploy a model. And some of that stuff can be quite time consuming or difficult to get the development environment set up right. With MLOps tools, that stuff can be a lot easier. So I'm going to show how you can very quickly train a few models to do sophisticated things. And then I'm going to point you at some resources to help get started doing this yourself. And we mentioned Edge Impulse a bit. So Edge Impulse, the company I work at, we've basically designed this end-to-end platform for training TinyML models. So I'm going to be using that as a showcase for MLOps. But bear in mind there are other platforms out there that do similar things. They're generally each sort of have a slightly different philosophy about like which aspects of this process are important. And so it's nice you can see broadly what these types of tools can do, but then given your particular application, you can go out and explore and find what works best for you. Obviously, I'm going to say that Edge Impulse is the best, but this isn't a sales presentation. So just this is going to be an example of a particular tool that does this type of thing. So I did want to say at the outset, please ask lots of questions. I'm really happy to answer your questions, and I'll leave it up to Vijay and Colby and our other hosts to decide how that works in terms of getting the questions to me. I really don't mind, so I'm happy to be interrupted at any point. If we do start running low on time, given what I want to present, I'll sort of speed things along. So, and then afterwards, I'm available. I'll have my email address and Twitter handle at the end of the presentation. All right, so without further ado, apart from having some tea, this is the machine learning workflow broadly. I stole this from Google's website. There are not many people who know more about machine learning workflow than Google. There are whole teams of hundreds of people working on optimizing the ML workflow at Google. They got some really good resources around like what this stuff is, how it works sort of at a high level, as well as low level things. And so if we walk through this, it's pretty simple. So you get some data, right? And then you have to clean up the data and figure it out. You code a model, you create a model in some way. You've then got to train the model, evaluate the model, and tune the model. It's all nicely encapsulated into one little block, but that's like could be years of work. You then have to deploy a model and then find some way to get predictions out of it, monitor those predictions for quality, and then manage all of the models and versions that you might have. So these are the steps of supporting machine learning in production. And that's the same whether it's on a big server somewhere or if it's happening on an embedded device. You might do more or less on each of these steps depending on the context, but that's roughly how it goes. So while you're going through this process, you're going to generate a lot of stuff. There's a lot of code and there are a lot of moving parts to think about. So I'm going to walk through, and I've tried to pick out most of them, but there'll be a ton of things I've missed, but let's go. So first of all, we've got some code that's capturing data. So you might be using a data set that someone's put on the internet, but most of the time you're going to be grabbing some of your own data at least and using that to train a model. So you've probably got some code that's capturing that data, whether it's from an embedded device or from some other kind of platform. You then need to clean up that data. So the raw data you capture is probably a bit messy, ugly. There might be things that are falsely labeled or just data that's corrupt, especially if you're dealing with large amounts. This becomes inevitable. And if you look at all of the big kind of academically published data sets, there are mistakes and discrepancies and duplicates and stuff that's misclassified. No one has a chance of getting this perfectly right. So this is always a big part of every data science project. As is data munging. So I don't know if you're familiar with that term. I love that horrible word, but it basically means taking raw data and transforming it in a way that makes it more appropriate to feed into your model. So it might be that the raw data, maybe you've got a load of images and they're all different resolutions and sizes and color depths, and data munging, the data munging process might be something you use to take that raw data and create a nice standardized data set where every single image is the same resolution and color depth. And it can get way more complex than that if you're dealing with like high level features that you're creating across data. And then you want to do some data exploration. Usually at the beginning of any project, you're going to look in and have a look at the data and decide, is it going to be worth trying to build a model around this? Like, does this make sense as a problem? Are there any signs as a data scientist that you can use to understand whether this is a important problem to, a fruitful problem to explore? Or can you just rule out that this isn't going to work right at the beginning? So once your data set is cool, you've got to start creating a model. So I usually for this will have some stuff in notebooks. I'll be throwing a bunch of Ipython notebooks together. They'll be all experimental, lots of commented blocks and weird stuff that doesn't quite work. And then from that, you'll maybe distill out some production training scripts. So these are the sort of like proper, real, like engineering artifacts that go into a system that can dependably train your model over and over again as you get new data, and if you want to add different iterations. So you've got a couple of artifacts that come out of just coding your model. And then when you actually come to train this thing, it's one thing if you're training on your laptop or on a single machine, but for bigger models or bigger data sets, you're going to often think about distributed training. So you're training across a bunch of machines. And so in this case, you've got to have some code which facilitates that, which can be quite complex itself. You've then got scripts that can help with hyperparameter tuning. So it's unlikely you're going to arrive on the perfect hyperparameters just by accident when you're coding your model. You'll actually want to do some experimentation. And so the scripts which code that, whether you're using a framework, something like Keras Tuner or HyperOps, or if you're doing things just by yourself, that is some more code, some more technical debt. And then once you've got a model out of the end of it, you're going to want to do some evaluation of that model. So again, it's the thing where you've got probably some notebooks to begin with that you'll be playing around with and figuring out good ways to evaluate the model. And then once you've got something down, you can bake that into a script which can be run in an automated manner. So all of this stuff has code dependencies as well. So you'll probably use Python, you'll probably hate dependency management in Python. If you don't, you haven't been using Python long enough. And all of this stuff is complicated, and to manage dependencies across a bunch of different computer systems that you're going to be using to train your model, that's a lot of work. We've then got model optimization code. So this is where we're getting into the TinyML part. So I've got a model. Am I now going to try and quantize it after training, or did I need to do some during training quantization, or am I doing something else to optimize this model? Are we utilizing sparsity and pruning, or what else am I doing to optimize my model? And that's super important to think about. Another big thing is the runtime framework. So maybe you're using TensorFlow Lite for microcontrollers, maybe you're using something else, maybe you've written your own, maybe you've got some custom silicon you're trying to run this on, and you've got to implement your own kernels. This is a lot of work. You then have to wrap this whole thing in an embedded application. So the model itself is no use. You've actually got to have some application code that runs the model within the context of the program you're actually trying to write that actually does something. And then you have to think about, do I even have space left anymore on my embedded device after I've got this big model? Do I have enough space in terms of both clock time and memory to run an application alongside it? And then once you've got this thing written, how do you build it and deploy it to devices reliably and repeatedly, and taking into account things like dependencies that are changing over time? And then once your device is deployed, presumably you're going to kind of want to understand what it's doing a little bit. So you maybe need some code that can help you log what the model is inferring on device, so you can test it out on device. You're going to need some kind of server for that to communicate with, because you don't have a lot of space on device to store the logs. And then in terms of the ongoing performance of the model, you want to have more code keeping track of evaluating, does this look like it's working right over time? Has my balance of inferences for this given problem started to skew in one direction, which is different from when the product first launched? Could there be a sign that there's some drift in what's going on in the data? You might need retraining scripts that do all of this stuff on a repeatable basis, so that you don't have to go through clicking ad hoc every time you want to update the model. And then build and deployment scripts, like maybe you've got a workflow where you're automatically pushing out the latest firmware to all of these IoT devices you're supporting. So you need more code there. And then there's even more. So you've got all of this stuff under source control. If you don't, you're crazy. So you have to use source control. But how are you going to structure this? Does this all go in one repo? Does it go in multiple places? Even your data should be versioned ideally. So your data set, as you add to it, you need to remember, what did I add? Because your model's performance is going to change, and you need to keep track of that. The data is part of your program, basically. The data is part of your code. So you need to keep track of how that's changing over time. And then you've got to do some automated testing to make sure all this stuff is working right. And then maybe you've got a CI/CD pipeline, which is continuous integration, continuous deployment. So this is sort of the dream for a lot of software platforms, where you commit some code, all your tests run, you know the code works, and it automatically gets pushed to devices or to users. So it's awesome if you can add this to your ML workflow. So I have a lot of post-it notes here. This is a lot to keep track of. And this is going to be, there will be some form of each of these post-its, plus more that I forgot to include, in every single actual production embedded ML project. So you cannot escape from all these things. These are the artifacts that the ML workflow produces in terms of engineering, in terms of code, that you're going to have to manage. And so there is a lot here. This is kind of crazy, overwhelming. If you don't have a system in place for keeping track of it, it can get very overwhelming very fast. And imagine you're working at a software company and you're supporting 5 different applications that each has this workflow for it. There's a lot to think about, a lot to manage. And the act of doing this is called MLOps. So whether you want to or not, whether you intend to or not, you are going to be an MLOps engineer if you are working on machine learning whatsoever, and especially embedded machine learning because it has extra steps. So the thing to remember here is that you can never get away from MLOps. You're already doing it. And so it is important to do it well, because this is what makes the difference between successful projects where you come up with a hypothesis, iterate through some solutions and get something working, and then are able to repeatedly deploy it, versus a nightmare where you can't compare the results of running different experiments because everything breaks in between. You have no idea what's going on, and you don't even know if your model is getting better or worse over time. So machine learning, MLOps stands for machine learning operations. I probably should have said that earlier in the talk. And essentially what it means is running the ML workflow end to end, managing the complexity that results, evaluating the results of your work, so making sure that you're actually doing a good job, improving your models over time, and tracking the deployments of your models so that you understand what is being deployed where when you're working with a production deployment of machine learning. So another way to think about this is this sort of what you should, how you should be thinking about this. MLOps is the ML workflow plus automation that you do to make that stuff manageable. Because if you don't use automation, if you don't use any structure, it's going to be an absolute nightmare. So when I think of MLOps, if I was recommending someone think about MLOps, I'd be recommending they think about how can they automate parts of their ML workflow to make their life easier. So there's a bunch of different ways you can do this. Actually, I should pause at this point and see if there are any questions.
One thing, Dan, maybe you'll get to it later, but it would be awesome if you can elaborate a bit more about the data versioning thing, because I thought that was an interesting point that you made, which none of us typically think about, or I don't think about.
Yeah, absolutely. So if you think about what you're doing when you're building a machine learning application, you're kind of cheating is how I think of it. You're like, rather than like, imagine you're building an application that can recognize whether someone is jogging or running or walking. Okay, one way to do that would be go and do a degree in something that is related to the structural biology of the human body and of the motions of running and walking, and study that and learn as much as you can about it and derive some rules that you can use as a heuristic to understand whether someone is running or walking or jogging. And then you would write some code which implements those rules and put that on a device, and there's your application. So you would check that code into source control, right? Because that's your rules that you've derived from all that knowledge and experience. So as ML engineers, we cheat at that process. So we take a bunch of data of people running and walking and jogging, and we don't necessarily know anything about the biomechanics of it. We just have a load of data describing it, and we train a model that describes or is able to predict whether someone is doing one of those things. And that essentially is our algorithm, right? But the model is not the source code for our algorithm. The model is our compiled algorithm. The model is like the binary of the algorithm. And the source code for our model it has two parts. One of them is the few lines of keras that you write to implement a like deep neural network with 3 layers that does this magic for you. And the other part is your data set, because either of those by themselves is completely useless. It takes them both to produce the model. And so when you think about writing source code as a professional engineer, you always keep source code under version control. So, and if you're not familiar with that, it's the idea of basically tracking changes to code over time. So you can go back and look through the history of what changed. So, you know, if I built something today and deployed it, it was based on this version of the code. If I make some changes and in 2 weeks' time deploy a new version, I can easily see which version the changes were from. So we need to do that with data too, right? Because data is part of the source code of our model. There is the potential that imagine you add a bunch more data. You've got like a new source of data, you add a bunch more data to your data set, you train a new model and you deploy it. And then you find out that customers are complaining and it's misclassifying their jogging as running or vice versa. You need to be able to get back to that old version of your model. And the only way to do that really in a reasonable way is to go back to your old data set. Because if you just think, oh, well, I have the binary model, that's all I need, you're not going to be able to add to that incrementally if you get new, better data in the future, unless you have the original data set. So that's why data versioning is so important. Another part of this data management story is if you're working with devices, you can actually do some cryptography so that you can understand which device data came from. And so understanding the provenance of your data like that, it's kind of like the farm to table idea with food, right? It's really good to know which farm did your egg come from? Because if someone eats the omelet and gets a bad stomach, you want to be able to know what the problem was. And so if you're able to do that with data and you keep track of where all your data samples came from, then you're going to be able to exclude them from future versions if something is wrong. So hopefully that gives a bit of an insight into that side of things.
Yeah, thank you.
Awesome. All right, so in terms of MLOps tooling, so there are a few different approaches you can take, right? And they kind of build on each other. So the basic thing you can do is write your own scripts to do this. So you can write your own scripts and frameworks that basically take all of these disparate artifacts and run them. And there's nothing stopping you just writing a load of custom code that can implement the whole workflow and automate the whole thing. And that's a good thing to do for if you're working on a small project, if you're working on something that's maybe not going to be around forever, but it's just something that you're doing a research project or something that has a small time frame. Custom scripts are going to serve you just fine. And this was state of the art until a couple of years ago anyway. But the next step is to think about things like frameworks. So frameworks exist. An example I gave here was TFX, which is Google's open source framework for MLOps. And essentially, frameworks are a bunch of code that has already been written that's designed to help you with this type of work. So rather than writing everything yourself, you can use these libraries that come as part of the framework to help implement different parts of your ML workflow. So that's great, but it doesn't necessarily cover everything, and you're still going to have to do a bunch of engineering work to sort of glue stuff together. So this is great if you're working on a big, ambitious sort of Google-sized project that you know is going to be around for a long time, and you need a lot of custom stuff, and it's going to need to integrate into your infrastructure. But there are a lot of cases that sort of fall in the middle where they're not a tiny ad hoc project, but they're also not Google search or something like that. And for those projects, there are a bunch of end-to-end platforms that exist. So Edge Impulse is one of these. I'm going to be showing you some of this in a moment. There are also a bunch more. And well, actually, there's not that many. There's like a handful more in the TinyML space. There are others in like mobile space, and there are platforms that are in the sort of server-side ML space as well, like Google's AutoML tools come to mind there. And so these take care of everything. So they start with ingesting data and managing data, and go through the process of training, evaluating models, optimizing models, figuring out how to deploy them to platforms. And this is sort of like the sweet spot, I think, for most engineers. So if you're not on the team of hundreds of people who are working on something that's happening in a giant data center for a massive tech company, and if you're not a single individual researcher hacking something for their PhD project, then an end-to-end platform like this probably provides the correct balance of flexibility with having annoying, tedious work done for you already. So a basic MLOps tool is going to have some way to manage and process data. It's going to have some way to train the models based on that data, some way to keep track of versions of those models, and some way to evaluate and compare models. And then when we're talking about TinyML, some way to deploy models to devices, and often for server-side ML, there'll be some way to host a model on an API. And so there are some big advantages to doing MLOps well, doing a good job of this. The first thing is that you're going to manage this overwhelming complexity that comes from dealing with all these moving parts. And you're going to reduce the knowledge burden that you have, which is the idea that, like, to do a bunch of things well, you need to learn a lot. And if you're trying to build a project around fitness, it's great if you can focus on learning a lot about fitness rather than having to learn a lot about how to write good Python scripts to do hyperparameter tuning. You know, it's like, as someone building an actual product, you want to focus on the part that benefits your users rather than having to learn everything there is to know about every engineering discipline that could feed into building your product. It also helps you be more scientific. If you can run experiments in a way where you control all the variables and you can keep track of the versions of models that you create, you can do this as a scientist rather than just toy around and experiment and think, oh, this is good enough. If you've got numbers to compare that are meaningful to compare because you can compare the same two models trained on the same data set, and you know that they were trained on the exact same data set, that lets you be more scientific. It also makes long-term maintenance a lot easier. When you've got some kind of framework or something that's well documented, people who aren't you can step into the project and easily understand what's going on and how to build on it. And I'm sure that most people here will have tried to download some source code from a ML paper and not even been able to get the thing to run because it is just really difficult to lock that stuff in. So one advantage of doing MLOps well is that other people can actually run your code and train your model, and then they have a chance of improving on it rather than just being stuck. And you can also monitor and improve your model's performance over time. So once you're tracking all this stuff, you can basically keep track of whether your model is doing its job well, and you can actually go in the right direction and make fixes. Whereas if you're not tracking this stuff, it's very hard to do so. So now I'm going to go on to the next part of this talk, which is going to be a live demo. So I'm going to give you a walkthrough of training models based on accelerometer data, audio data, and image data using an MLOps platform, which happens to be Edge Impulse. So I'll show you some of the features of Edge Impulse and how they map onto what we've talked about. But before we do that, does anyone have any questions? All right, so let's get on with checking out some stuff. So I'm going to go first of all to this project. This is always our sort of hello world project. And it's basically gesture recognition. So I don't know if my screen font size is readable. How is that for everybody?
Looks good.
Okay, perfect.
Again, can I just quickly add one point?
Mm-hmm.
So for the students, one of the things that, one of the reasons we have Daniel talking about things at this critical point about Edge Impulse and MLOps is because you're working on your project proposals. And, you know, one of the reasons we're having them here is so you might be able to see how a framework like Edge Impulse is actually going to be useful for doing some of your projects. So just kind of keep that in mind. So the examples and so forth that Dan's going to go through might actually be very relevant for some of the your project stuff. So it might be a framework that you'd want to use. Just want to mention that, Daniel, for the students. So.
Yeah, awesome. Thank you, Vijay. And yeah, totally. So I'll sort of try and speak to that as we go through as well. So what I'm going to do is show you these three different, working with three different data sets. And basically the way that the things I've chosen, we also have tutorials and videos for. So I'm going to whiz through this super fast, and I'm not going to step through every step of the way as if I was starting from scratch. I'm going to more just dive in and show you interesting stuff. But all of the stuff I'm showing you, we have video tutorials on the documentation, and I'll give you some links to that as well. And we also have written tutorials for people like me who can't handle videos. So first up, I'm going to show you this demo of doing gesture recognition. So gesture recognition, if you've read the TinyML book, it's like the magic wand stuff where you're doing some kind of physical gesture and picking it up with an accelerometer. And so what I've got here is an Arduino Nano 33 BLE Sense board. It's connected via USB to my machine. And I've got this project open in Edge Impulse. So you can see, just as a question, can you see all this like Zoom UI that's also on my desktop covering things up? No. Okay, that's awesome. So we're on here on the dashboard. So this is just the front end of the project. Nothing that exciting here. So I do want to show you that like you can download a lot of interesting stuff once you've trained a project in Edge Impulse. So all the things you're familiar with, like TensorFlow Lite model files, saved models, all your data in different forms, all gets managed by the platform here. So you can grab that if you need. But what we're going to do is first of all, jump into data acquisition. So everything starts with a data set, right? And here we have a data set with 6 different gestures that we've trained. So there are gestures like idle, which is when the device is just sitting there doing nothing. Snake, which is like doing a sort of snake-like movement around. We've got up, down, which is going up and down like this, and a few others. So what we've done is we've used Edge Impulse to capture samples of this data, of these actions. And we've actually grabbed those directly from device. So Edge Impulse can basically accept any kind of data, whatever type of data it is. There are ways to upload it. But what it can also do is connect to certain devices and capture data directly from the sensors. You can also use the SDK. If you've got a custom device or something that's not natively supported, you can just write your own code, use our library to send data into Edge Impulse. So what I'm going to show you here is capturing data from the Nano. It's super easy. So if I open up my terminal here, I've got this thing running, which is the Edge Impulse daemon. And if I run this, it just runs a little program that connects to this board. The board has some custom, pardon me, it has a custom Edge Impulse firmware flashed on it. It connects to the board over serial, and then you can control the board from the Edge Impulse web UI. So I'm going to capture another sample of up, down. So if I click start sampling, and I'll just start going up and down. All right, so it captured some data, and you can see my 3 accelerometer axes there, X, Y, and Z. And you can see the motion reflected on the Z axis. So all of these data samples were captured in the same way. So we've got a bunch of up downs, we got a bunch of others. And you can just add more data here in that manner. You can also upload it. You can upload from the web UI. We have command line tools. You can put it in Amazon S3, pretty much anywhere you can think of, you can get data in. So once you've got the data, oh, and also we have, you have a training data set and a test data set. And you can either manually manage these so that you make sure that you have the correct sort of 20%-ish split for a normal size data set, or you can have Edge Impulse manage that for you, where we automatically split the data as you upload it. One of the things we do here is also look out for any type of duplicates or corrupt data, and we'll help you avoid having stuff like that that can pollute your data set. So the next section is where you define what your program is going to do. So Edge Impulse basically outputs a library. So you're gonna do all this work, and you will output a library which is optimized to run on a particular device. In fact, it uses C++ compiler magic to optimize itself for whatever device you're currently targeting, whatever device you're building the library for. But the library will basically take raw data from a sensor as input, and it will do some signal processing on it, it will run inference on it, and it will give you an output, which is basically a set of probabilities for a bunch of different classes. Right now, we started out building this tool around classification. We're going to add support for regression and for really complex structured outputs, so we can do things like object detection in the next couple of months. But right now we're focused on classification because that's what most people tend to want to do with embedded ML right now. So this screen here represents your impulse, which is what we call a chain of signal processing and machine learning. So it starts with this input block here, which determines how you window your data. So windowing is basically the concept of taking a chunk of data that represents a certain amount of time and feeding that into a model. So our window size here is 2 seconds, right? 2000 milliseconds. We've got a window increase of 120 milliseconds. So what that means, if I've captured a 10-second sample of data, that's our raw data, right? And then to create our actual training set, what we're going to do is take 2 seconds off the front of that 10 seconds of data. We're going to take that will be one sample. We'll then move along by 120 milliseconds, and we'll take 2 seconds worth of data, and that will become our next sample. And we'll keep doing that until we get to the end of the sample. And so that's how we sort of take our 10-second raw chunk of data, and we might have a bunch of different ones. Like in here, we've got some that are 3 seconds, some that are more, some that are 4, some that are 10. We're cutting those up into same size pieces. And what we do with those is then do some signal processing. So you probably kind of understand by this point that it's very rare really that you're going to pass raw sensor data into a deep learning model. It's generally most efficient to do a bit of feature extraction beforehand. And so we allow you to do that. We have a bunch of feature extraction blocks that we've implemented here. They will take your raw data, do high-level feature extraction on it. And those are implemented both in the cloud, where the platform runs, and on device. So here I have a spectral analysis block, which is very useful for dealing with this sort of time series signal. When we deploy our impulse, the implementation of this signal processing code will also be exported along with the model. So all you need to do is call one function, and it will do the signal processing and run the model. We then have a couple of different models here. So rather than I guess I could talk about the basic one first. So we have a neural network block. So this takes our signal process output, and it runs it through a neural network that we can define in the platform. We also have an anomaly detection block. So what we've thought about here is that, if you pass a deep learning model data that is nothing like anything it's seen before, if it's a model that's trying to do classification, it's just going to try and shoehorn that into one of the classes it knows about. It's not able to understand, oh, I haven't seen this before, because of the way deep learning models work, at least these types of deep learning models. If it wasn't exposed to something during its training, then it's not going to be able to understand what it was, and it's going to give some kind of spurious output. So we actually put an anomaly detection model using k-means clustering alongside our deep learning method, our deep learning model. And this is going to screen our inputs and understand whether they are similar to the inputs that were in our training data set. And that means that if we know that something wasn't similar to what was in our training data set, we know it isn't one of the classes that we care about. So we don't even bother feeding it into the deep learning network. So that saves us both time when we're running the algorithm, and it saves us from having spurious results from our deep learning classifier. So these are both things that are super easy to train. So first of all, let's look at how this DSP stuff works. So essentially the spectral features block, it's extracting a bunch of useful high-level features here. So I won't go into the details, but we're doing things like running an FFT. We're looking at, we're doing some filtering, and we're extracting a bunch of different features from this, which you can then see. Oh, and just to show you, this is the display of raw data here. This is one sample. So this is like 3 seconds long. Here is our 2-second window. So I can drag that around and see how different parts of this sample would be reflected in different features. And so if I go to this tab, remember I talked about exploring your data. So on this tab, we can look at the high-level features that were extracted by this block. So for example, the x-axis root mean square feature that we've calculated here, we've got that graphed against the y-axis and the z-axis. Remember, we've got 3 accelerometer axes here. And when we graph these, we can see that if we add a dot for each of our samples, you can see very nicely that these samples can be clustered. They can be seen as discrete groups within our data set when you look at these RMS values. And so by looking at this, you can immediately understand, hey, this is a problem that is going to be feasible for a deep learning network to make sense of, because as a human being, I can figure out where to draw lines on this in order to separate these. So if I can do it, hopefully a multi-layer neural network is going to be able to as well. Okay, cool. So once we've basically figured out that we can separate our data here, if we can't, we can go back to the drawing board, and maybe if these all appear in one big uniform blob, that's a sign that our data can't be separated very well. So it might be worth going in and tweaking some of the parameters here and seeing if we can get a better signal out of our data. And we do basically a bit of iteration here until we have something that works. And so once we've got something that works, we can start working on our ML stuff. So first of all, I'll hit the ML classifier. So this is going to take the output of our DSP block, and then it's just got a 2 dense layer network here. Super simple. And what we do is basically hit train. It will train this network in the background. And once the network is trained, I'm not going to do it now. This will only take a short time, but I want to get through some other stuff, so I won't even wait for that. But the performance of your network is then given here. And you can see here, we've got like really probably suspiciously high accuracy. There's probably a bit of overfitting going on here. But you can see a confusion matrix of all of our classes and how the samples have been sorted by class. And there are no errors here, which that's usually a sign that things are a little bit too good to be true. Maybe you want to reduce the capacity of your network a little bit, because you might not get as good results as this on your training or your test set. So this is data from the validation data set. So when you run training here, we automatically split your training data set into training and validation portion. We'll run through training and then we'll generate a model, or output a model. We also apply optimization. So here we have a couple of one type of optimization available, which is quantization. You can also access the float version of the model, and we can compare them. So if I look at the float 32 version of the model, it has 2 milliseconds inferencing time. It takes 17.5K of RAM. The quantized version, it's a bit faster and a bit smaller. Once you're working at this tiny size of model, the overhead in the supporting infrastructure for the model is quite a large proportion of the thing overall. But this is the actual amount of memory that the entire model and all of the operators that are used to implement it will take up. And this is the amount of RAM that's used by that. So you can use this alongside your application code to budget. How much space do I have for the tiny model that I'm going to have on this device? And you can see whether there might be some differences in performance between different versions of the model, and you can compare those side by side. So if you want to get your hands on a bit more, so one thing you can do is basically adapt this model as you see fit with our GUI editor here. So I could add another dense layer, 10 neurons. I can then move that around within the model. So that's awesome. For a lot of cases, that's just going to work fine. But what I can also do is switch to Keras mode. And I then get a little code editor here, which implements the model. It looks a bit ugly because my font size, but you can go in here and control everything. So if you want to write your own custom loss function, or if you want to adjust some of the hyperparameters that we don't expose in the UI, you can do that, and you can really go crazy there. And just to make experimentation even easier, you can actually download an Ipython notebook that implements the whole pipeline. When you run it, it will grab the data from Edge Impulse, run all of your model code. It won't upload the model back into Edge Impulse. So what this is useful for is basically doing a bit of, if you needed to do some hardcore iteration on your dev machine using a bunch of other tools to get the most out of your model, you can do that, and then you can paste the result back in here, and we'll take care of running it for you next time it runs.
Just a heads up, we got 10 minutes.
Okay, wow, I need to speed things up a bit. Sorry for spending so much time on the earlier sections. Okay, so anomaly detection here. This works a little differently. So we've got our own implementation of k-means clustering, which basically identifies clusters in samples and is able to basically score a given sample on whether it falls inside of or outside of a cluster. So here you can see we've identified these 3 axes we're going to do the clustering on, and you can see a visualization here. This is how our data set looks. And so if we were to add, if we were to do something that falls outside of the data set, it would fall outside of these clusters. And we know that we wouldn't be able to rely on our deep learning network to make sense of it. So you add this, it trains, you get a nice implementation of this in the library that comes out of Edge Impulse. All right, so next thing to look at is live classification. So here you can test out your model's performance based on data from the device or from existing samples. So if I capture a sample of myself going up and down, all right, so you can see here, my shaky hands have resulted in some misclassifications. So here I got 3 of these samples. So we can see how this is the whole sample here. It was broken down into different windows. And you can see 3 of them here were successfully classified as up, down. But some of them were not. So these ones were below our threshold. So up, down was still the top category, but it was below our cutoff threshold of 0.8, which is configured in the classifier block. These ones were interpreted as drink. So this was a different gesture. And so this suggests maybe I should add this particular sample to my data set so that the network, next time it's trained, can better understand that this is an up, down, and not a drink. You can also see how these new samples appear on our feature map here. So you can see them down in this section. They are obviously not clearly inside of one of the clusters. So this looks a little bit different from what our model would expect, but it did fall within these clusters here. So it is not being recognized as an anomaly. So a big important part of deep learning is verifying your model's performance on data that it wasn't trained on. So the stats in the NN classifier block come from the validation set, but here we're in a different view where we can run our model across the test data set. So if I click classify, it's going to basically window all of our test data, and then it's going to run inference across all of the resulting samples using our model. and then it's going to give us some results. So we've got 99% accuracy on the unseen data. So maybe our model isn't too overfit after all. That's pretty awesome. And you can see for these ones, they're green because they were correctly classified. Here, this one, if I click on it and go to classification, you can see that it was misclassified. Some parts of it were misclassified, and we can see what happened there. So these ones registered as an anomaly. So these were caught by our anomaly detector. So if this was a reasonable sample, maybe we'd want to add more samples that are similar to this one. You can actually see from the visualization here that it's got a bit of ugliness at the end. So actually, maybe this isn't a great up-down sample and we should delete it from our data set. Okay, so running out of time, I'm going to quickly go through some stuff and get onto these other models. So versioning, you can create new versions of your model or your project, and then you can go back to those if you want. So just click a button, add a description, create a version, and then you can revert to those if you need. When it comes to deployment, you have a lot of options. So the default here is to deploy a C++ library. So this contains all the optimizations you need. We do this magical thing we're calling Eon, which basically we do some code generation, which uses code from TensorFlow Lite for microcontrollers, plus some of our own code, and generates a big single static bundle of code, which rather than using the TF Lite interpreter, it just implements the model. So you save some ROM and RAM in using that, and latency improves very slightly. So we'll output a library with that in. You can also switch that off if you want something that uses TF Lite vanilla. And then we also support some other targets. So for example, STM32Cube AI for ST boards, they provide a library which you can use for doing fast inferencing. So we will make use of that. You can do an Arduino library, or you can output pre-built firmware that will allow you to test your impulse running on devices like the Nano sets. All right, super low on time here. So I'm going to show the same for audio. So for audio, we have a data set here of different types of bird. So I've got a mourning dove. You probably won't be able to hear this if I play it. Let's see. Anyway, I've got a few other species of bird. In this case, I'm using an MFCC block, which is another signal processing block we support. It's generating a spectrogram, which you'll be familiar with here. This is the same block you'd use to do a keyword spotting. In fact, I have an example of that here, which is doing yes, no, and noise. So here, the same deal. We just create a different type of network. So for audio training, we also let you do some data augmentation. So you can enable this and automatically add noise and morph your input to the model so that your resulting model will be more robust against variations. So that's good if you've got small data sets. I've defined an architecture here, but we also have preset architectures that we decide on that are recommended. So for example, here's a recommended 2D convolutional network for this data set. And here's a recommended 1D convolutional data set, model architecture, sorry. So once you've trained your model, you can end up with some really small stuff. So this is getting like 78% accuracy, still only using 32K of ROM. Remember, that's inclusive of all of the accessory code as well. And we're using 11K of RAM and getting 38 milliseconds inference time. This is on a Cortex M4 board. If you go to the dashboard, you can choose a few different devices that we provide latency calculations for. So we also support vision. So here I have a data set of cars. This is what I use to help benchmark our model performance because it's actually a pretty hard data set. So I've got different types of cars, and what we try and do is take a 96 by 96 version of this image. So we'll shrink that down for you. You can resize in different ways. And then I turn that, actually, I think I'm using RGB here, but I could make this grayscale if I wanted. This is really cool because to explore features for things like images, we actually use a algorithm to map the data into high dimensional space as an embedding that lets you explore whether the data is separable in this sort of high level where I don't really have time to go into how that works. But you can see here, there is some skew in where these things are. It's a little bit more visible with the audio data set. So you can see we've got this big blob here, but it's more orange on this side and more blue on the other side and more green in the middle. So this gives me a good sign that a network will be able to start to tease these things apart. This is using visualization algorithm that is, actually, I can't remember which one we use, but I can give you that information afterwards. So same with vision. You just train a model. Vision models can be, oops, that was the keyword spotting. Vision models can end up a bit bigger and take longer to train. So we also support transfer learning for image models. So here you can get a tiny mobile net, which you can train on this data set using transfer learning. So it takes hardly any time to train, even though it's a relatively large model. You can see this takes up about 600K. It takes around 1.2 seconds to run on an M4. We're not getting great accuracy with this, but that's because this is my super hard, low samples test data set. So I think we have 1 minute left. So I'm going to cut myself off and go back here. So my big takeaway for you is that you are always doing MLOps, whether you want to or not. So please make sure you do it well. If you do it well, you can treat this work as you would any other science. And if you don't do it well, you'll be treating it like I don't know, just managing chaos. So the better you do your MLOps, the better results you're going to get from your models at the end of the day, and the less you're going to pull out your hair. So thank you very much for watching. You can reach out to me with any questions, dan@edgeimpulse.com. I'm on Twitter, Dan Situ. We have a forum for Edge Impulse. So if you end up using Edge Impulse for any of your projects, we're really responsive on the forum. We answer questions within a few hours. So anything you might want to ask, jump in there. We also have tutorials for a bunch of different sensor types that are in our docs. So I'm sorry I sort of overran my allotted time by waffling a lot at the beginning, but I'm happy to answer any questions you might have via email if we don't have time now.
Thank you, Dan. That was awesome. Are there questions?
Yeah, that was great, Dan. Thank you.
Thank you. And yeah, thank you, all of you. I'm super excited to see like a whole generation of people who are jumping into this field, and it's going to be amazing to see what you all end up building and contributing. So very cool.
Yeah, this is great. Yeah, this is like one of those software engineering practices that you never ever think about. You know, you just write your code and yeah, it would work. And you're often trying to beat it into the students, like, damn it, you got to use versioning. You got to like comment your code.
Yeah, so this is one of the things, because I'm a software engineer who became an ML engineer. I'm not someone who came from sort of the like academic ML world. And that means that when I see some of the engineering practices in some of the code that gets shared with like really respectable ML papers, it makes my skin crawl. And especially when I try to re-implement or run some of the code that people share, it's absolutely crazy. So the more you can get a handle on MLOps, the better you'll do, not just if you're building production apps, but as a researcher, if you can bake some of this stuff in, then people are going to be able to reproduce your research a lot more easily, which is always important.
Yeah. Awesome. Well, thank you again, Dan. So for the students, you're welcome to stick around if you have questions or